Okay, it is time to leave the diols behind for now. We've had enough of our little cyclohexene ring forming fun. Now let's look back at redox reactions. So we've gotten the diols down in droves. You should be able to predict the stereochemistry, predict the regiochemistry, and we'll do a little bit more with synthesis later on. But basically, now we look at these oxidations because they, like the diols are pericyclic reactions. The mechanism is the same. It's all about orbitals and a concerted kind of reorganization of pi electrons to form new bonds. So it's pretty cool. The one we're focusing on specifically in this mini lecture is the formation of syn diols, dihydroxy groups, from alkenes. But first, let's review redox. Redox in organic chemistry. So we've seen this little schematic before, that if we start out with some pi electrons, like an alkene, we can reduce them by adding hydrogen across the double bond. That's a reduction. And what we would do is, add H2 and maybe a palladium catalyst. Now we're going to look the other direction. We're going to look at oxidations. And basically it's pretty easy to see as there's an oxidation taking place. Instead of adding hydrogens, we're adding oxygens. So let's hammer this point home by actually looking at the change in oxidation states for this particular transformation. So if we look at our starting alkene, we can see that both of these carbons are identical in terms of oxidation state. So the oxidation state would be figured out by looking at what's attached to the carbon. So we've got two hydrogens that are +1 and a carbon which is 0. So +1 and 0, that means each one of these carbons must be in the -2 oxidation state to keep everything balanced out. So we've got a +2 oxidation state for each carbon on the left. What about on the right? Well, on the right we have a substituent that contributes a -1 charge, two hydrogens each at +1, and a 0. So the oxidation state here must be +1 +1 -1. This must be -1. And I know I'm going through this pretty quickly, so you might want to confirm this on your own. But basically what we're looking at is going from two carbons at oxidation state -2 to two carbons at oxidation state -1. That clearly is an increase in the oxidation state, and hence we know we're undergoing an oxidation. So what we want to know now is what'll do that. And we've already learned about reducing agents. You're adding hydrogen, so reducing agents are things like hydrogen gas or zero valent metals, because those zero valent metals, like sodium, they like to be oxidized to, say, sodium +1. So reducing agents like to be oxidized. Well, what does that mean about oxidizing agents? They like to be reduced. So just as we can look at reducing agents and see, woohoo, we're adding hydrogens, oxidizing agents, look at all those oxygens. So that's a dead giveaway that it's a good oxidizing agent. Another dead giveaway is that you're talking about metals in very, very high oxidation states that really, really want to be reduced. So we'll see that in the reaction we're focusing on in this mini lecture, this dihydroxylation to form syn 1,2 diols. So the reagents that do this are generically these guys. That M stands for metal, and the two metals that we look at in this chapter that will carry this out are osmium and manganese. So it's actually osmium tetroxide or permanganate that does this. And so the important message that you need to get mechanistically is kind of given as an overview on this slide. So you have your metal with all these oxygens around it. The first thing you can do is say, holy cow, with all those oxygens around it, I'm pretty darn sure that metal is in an extremely high oxidation state. So yeah, MnO4. So we're talking about potassium permanganate. That means we're talking about 1, 2, 3, 4, 5, 6, 7. We're talking about manganese in the +7 oxidation state. You had better believe it wants to be reduced. So it is dying to suck up some electrons, and looky there, there's some electrons ready to be oxidized in that alkene. So my oxidizing agent really wants to be reduced, and as it approaches the alkene, let's just do that again. It approaches the alkene, woohoo! And that sets up the key pericyclic mechanism where my pi electrons actually attack one of the oxygens, give the pi electrons back to the metal, reducing it, and then the pi electrons on the other metal oxygen double bond react to make an intermediate. That intermediate is then hydrolyzed in some magic mechanism chemistry that we don't cover, at least not yet, to give you the syn diol. The important message here is this happens all at once, and we get exclusively the syn arrangement, the two hydroxyl groups on the same side of what was the double bond. Alright, so that's really going to be emphasized in this mini lecture, stereochemistry. So it happens all at once, and it's that concertedness that makes it give you the syn stereochemistry. But there's another point I want to make here too, and that is that osmium tetroxide is actually the preferred reagent, but it is a terribly, terribly toxic reagent. So it stands, well, it stands to reason. Researchers have developed a method where you can use the osmium tetroxide in just a catalytic amount. What this requires is the addition of another oxidant to just keep reoxidizing your osmium tetroxide. So here's a nice example of a real application of this chemistry. The researchers were trying to make this particular target molecule, and what you can see here is that there's my syn diol. But one thing that OChem textbooks are notoriously bad about is reality. Okay, if I really want to carry out this reaction, how do I do it? The book doesn't really tell you. It just says use these reagents. Here's the reality. You have to basically take your starting material and dissolve it up in some specified amount of solvent. You need to specify how much of your starting material you're using, and then you're going to add this much of the co-oxidant, and look at this. Wow! Only one crystal of the osmium tetroxide is required. And then basically you let it run, you let the reaction run overnight, and then how do you purify it, and that's all this stuff. So man, it's not as simple as it seems when it comes to carrying out this chemistry. This is just a point to make the point that, you know, what we show you in OChem lecture is what you need to know in order to go from A to B, but it doesn't actually let you go up into the lab and do it. Alright, well, let's look at a real example again with a little bit more on the mechanism for explaining the stereochemistry. So here is, in fact, the osmium tetroxide that's going to give me the syn stereochemistry, and here is my co-oxidant, hydrogen peroxide. Hydrogen peroxide is a pretty safe reagent to use, so that's a good choice. All right, well, what's going to happen here? Well, as my osmium tetroxide reacts with my alkene, I'm going to get syn diol. Now, it can approach from the top side of the alkene, and that would give me this guy. Then how does this one get formed? Well, that one will be formed from approach of the osmium tetroxide from the bottom side to give you this particular intermediate. These intermediates are the osmate esters, And as I kind of alluded to earlier, it's some kind of magic chemistry that we don't know yet that allows these things to be cleaved and leading to exclusively the syn diol. Okay, so the key things you're looking for here: pi electrons, electron-rich, heavy-duty oxidizing agent, lots of oxygens, syn. And all you need to think about with the mechanism is, yes, we've got, well, let me clean that up a little bit. We've got these guys, 1, 2, 3. One swell FOUP, it happens all at once to give you the syn intermediate, which gets cleaved to the syn diol. All right, so let's hammer that home even more. Here is an alkene with a specific stereochemistry. We have the Z alkene. Addition of my oxidizing agent that has the specific mechanistic requirements of syn addition would not give me this. Okay, so this is not going to happen. Well, says who? How do we know that doesn't happen? Okay, so if I take my Z-alkene, do I get two products? Well, if I got both of these products, I would be able to tell, because they're diastereomers, and we know that diastereomers have different physical properties. Okay, but it turns out, experimental data, we take the data, we look at the evidence, and we say, oops, we don't get any of that. Now I'm just going to put in a little interjection here. I want you to look carefully. That looks syn, and it's not. That is the anti-product. So you need to think about why that really is the anti-product. But the bottom line is, it doesn't form, because the evidence says it doesn't form. Because the evidence, the experimental evidence says we do not get any of that diastereomer, that implies that the intermediate that would allow the formation of that diastereomer, where somehow or other we get our osmium tetroxide to come and dump in an OH group on either face of that p orbital, this would clearly lead to syn, and this would lead to anti. Well, if that carbocation intermediate was formed, we would expect to see both stereoisomers, and we don't. So that implies that that carbocation intermediate is never formed, and that's part of the experimental evidence that proves to us that this must be a concerted mechanism. So, synthetically, now we've got another tool for our toolbox. If we want to make a diol, we now have the tools to make either the anti-diol or the syn diol. So the anti-diol we can make by going via the epoxide, and we know how to make that. We make the epoxide by adding a peroxy acid, and then we can add water or hydroxide to ring open with anti-addition, ring open the epoxide to get the anti-diol, or now in one swell FOUP we can go to the syn diol using catalytic osmium tetroxide or potassium permanganate under pretty mild, cool, basic conditions. So add that to your synthetic toolbox, because we will be seeing it again. Next up, another incredibly cool oxidation where we tear apart a double bond and plop a couple oxygens on, chopping things up by ozonolysis.